Right. Sorry for that. Is there anyone out there who can verify my sound? No sound? Yeah, great. It would be quite fun if someone actually in this room answered my Slack call and answered, yes, we can hear you. Exactly. So, sorry for that delay. Some setup problems here. So, today's topics are logical and physical modeling. If you have had a chance to download the PDFs, you will notice that there are some 120 slides in total. I will not use them all. I don't think I will use more than half of it. Some of them don't really apply, and I'll correct that later on. So, also there are 2 PowerPoint files for today, and that is due to some of my changes in the older presentation. So after a while I will flip over to the newer one, and then I will revert back to the older one. But I will let you know when it's time to flip presentations. Okay, so let me change the batteries then. Or is there someone in here who... So that was the final battery. If that's impossible to hear me, or perhaps it's just one of you. All right. Okay. Okay. So that image you have seen for a while now, and we're coming up on the final stages here. Where we should be starting to transforming our model into actual tables, and also try to normalize them. And there will also be a shorter discussion on what happens, or at least how you should think in terms of how much memory your table will contain in the end or after a while. A bit of just to predict things here. So those 3, that's what you have been doing for a while right now, 1 and 2, and at least partly 2, that will be discussed today, and also the 3rd one, which is the normalization. But we need a few new words here to describe what we should be doing today, and the first thing here is the functional dependency. And the functional dependency means that you have a set of attributes that depend on some other attributes. And for those of you who have been studying this before, usually you want your some of your attributes to be determined or being dependent on your key, and that is what they are usually talking about in these relations. So we have that dependency x pointing at A, so that is the constraint between those two sets. So the attributes in the set X are said to functionally determine the attributes if in another set A. The key is usually and should determine the rest of the non-key attributes. That's what they're saying here. There are also versions of this when there are parts of your non-key attributes also starts to determine or being function dependent on other non-key attributes, and that is also something that we shall be talking about today. So if what they have in the last paragraph there is that if you know the values for the attributes in the set X, then you can always find the attributes in the set of A. So it sort of points out. And there are a few different kinds of these function dependencies. So the trivial one is when the part that is pointing at itself, and that is always true. And then you have the non-trivial version of those functional dependencies, and that is when that functional set X or part of it is pointing at the other set A. And the other one is the non-trivial one, and that is when you have the X's pointing at nothing in A at all. So the easiest way to have a look at this is to just have an example. So the first one to be said here is that if you have the ID is determining itself or is functionally dependent on itself. That is always true. It doesn't matter what. The same thing here is also true for the body score. That's the one set that is determining the own set of itself, which is the body and score. So you need to see these as sets of attributes being functionally dependent on other attributes, and the other way around is when it is determining other attributes. Sometimes, or usually, you need to know where you are using your attributes, and that is the domain. You are supposed to use your relation or your table for something, and you also need to know the domain of your values. So when you know that, you also know how functionally dependent your attributes or your sets of attributes are. So just sitting down and making those guesses that you do is not something that is trivial. So if we try to find an attribute, and this is something that I have actually been talking about before, if you find something that can uniquely identify a row in a table, then you have that attribute, in this case, being ID. And that ID attribute is in that case a sort of a key. And that ID, or that attribute ID, can uniquely identify each and one of the combinations of the set of attributes being ID, body, score, and created. But since ID always can always sort of point out itself in this case, we can remove the ID from the set of attributes that it is determining. So ID is determining body, score, and created. Which means that each of those, body, score, and created, are functionally dependent on ID. And that is also a way of looking at it. So ID is determining body, it is determining score, and it is determining created. And ID is the key that makes this thing work, because it is a unique thing here. That's the key. So if you have a set of attributes that you can say are making a row or another set being exactly unique, it can exactly point out a definite row in a table, then it is a key. So that set of attributes named X here is what is called that key. So that key can be composed of one or more attributes. The key can be composed of one or more attributes. The last paragraph here stating that a key is minimal if there is no proper subset of it that is also a key. Well, you can always make that key larger than it needs to be. And if you have made a discovery that it is not possible to make that key smaller, then it is minimal. So that is a way for you checking for functional dependencies, ruling things out. And there's also a thing called candidate keys, because sometimes you might find multiple keys that are actually working. So then comes the decision for you to make whether you should use which one of these candidate keys you should be using. So this is what I told you earlier. You will probably find out that ID is a key. And the case here is that what ID is determining is the entire set of that comment attribute. So what you can do is that you can remove the ID from the right-hand side here, because it is always functionally dependent on itself, in that case when it's the key. So you just remove it, and then you end up with that ID is the key for body, score, and created. And that means also that it's the minimal key. If you have created a key that is larger than it needs to be, then it is a part of the super keys. It might not be that common to talk about super keys. When you start to think about these things, you want to find just a key, or at least a few candidate keys for your relation or your table. And when you were talking about those candidate keys, and those candidate keys could be 2 or more, or at least 1 or more. If you select one of these candidate keys to be the one to use, then that candidate key is the primary key. So from the set of candidate keys, you decide to use one of them, then that key is the primary key. And the word or naming something a primary key is something that you also will see in your SQL server, because you will name one or more columns as the primary key. So just remember that sentence here, the primary key, or that definition, sorry. And finding keys is sometimes really hard, because if you don't understand your problem, if you don't understand your domain, you might be selecting the wrong combination of attributes as your key. And if you let your system loose and you figure out after a while that, okay, I am actually adding new entries into that table, violating the constraints set by the primary key, you have to rethink your model once more. So that is not something that you want to be finding out after you have released your database. Okay? So there's usually a lot of discussion going on when you are to decide the primary key of relations. And I think I mentioned earlier that thing about creating artificial keys. When you start to add keys because you don't have one and you can't find one, that passport number, that's an artificial key. Employee number is another one. So when you are to set your keys in a model, you underline your attributes, and when it has an underline, it is either the key or it is a part of a key. So in this case, the entity comment has ID as its key, and and user has name as a key. And those keys and a few constraints. So I already mentioned that the word or the definition of a primary key is something that you set in your database. You can also use a constraint named not null, which means your attribute is not allowed to contain a null value. So if you try to add one, the database will kick back at you. It will display an error message. Primary keys are not allowed to have null values in them by default. And then there's this keyword unique. It doesn't mean that it's a primary key, but it means that for an entire attribute, there can only be a single value for a specific domain. So if I'm adding my name, let's say, or someone else's name, Leia, in the column of name, then Leia may never appear once more. It can never appear again in that column name. But it's not the primary key, because the primary key points out a row uniquely. So just remember that unique thing, because sometimes it comes in really handy. So creating that table using that syntax tree or that syntax diagram, you can follow it through here. You will find that there will be a few table constraints, and there will be a few constraints on the column. And that is for you to use to mark one or more attributes as a primary key, or as a unique column. And those constraints are not that hard to use. It's a lot harder to figuring out why they should be used. That's the model thing. So if you reach this stage where you are to set your primary key when creating a table, you already know the keys here. You already know which columns should be unique and all that. It's just a matter of typing them into the console and sending it to the database server. So if you are creating a few tables here, user, comment, and posts, you could have a look at that last table, posts. As it is right now, there are no primary keys at all, so you can add any combination of rows here. There will be no checking for uniqueness whatsoever. So if you need that, and you need to do that on the post table, then you specify that by issuing that primary key command. So what you do is that you just print out primary key, and then you add your columns that should be a part of that key. So in this case, it's username and comment ID. That is the primary key. And it is also the entire table. Right? Because if you, let's assume that you set username as the only part of the primary key, then there would be only one comment per user. Or even more strange, setting the comment ID perhaps, or something, as your primary key. So if you're adding them both as a part of the primary key, everything will be well, at least for now. And the next thing here is the concept of foreign keys. So the primary key is uniquely identifying a row. The foreign key is referencing a key, or at least a part of it, in another table. The foreign key references another key in another table. And that makes this sort of good, because you can make an association here. You can move from one table to another, and your constraints are enforced. You cannot reference anything that doesn't exist by using foreign keys. So let's assume you have your comment table, and you have your author ID. That's the author of the comment. You don't want to store everything about that author in that comment table, so you're better off having your author information in its own table. But if you are looking at your comment and you need to get more information about that author, then you make that as a reference. And by making a reference, you are guaranteed that your comment doesn't go without an author. So an author has to exist before you make a comment. That's important. So using the foreign key construct here and naming your attribute, the one that should reference, and then use the words or keywords references, which table and which attribute. So author is referencing the attribute name of the table user. So you have effectively added a constraint here. So once again, you cannot add a comment without an author in that table user. And this is good. Just imagine if you didn't have any keys at all here, you didn't have any references, you could just about do anything with your tables. You could add null values, you could reference things that doesn't exist, you could have multiple instances of things. So what you see here is good. Some people find it really troublesome doing these things because when they are doing their programming, they are getting a lot of exceptions thrown because they haven't figured out how to use the database in an orderly fashion. So it's easier to not set any keys at all because your program works without exceptions. But logically, it doesn't work. So if you see a set of tables without any keys at all, no primary keys, no foreign keys, then you should question the model. Why is it as it is? And that is what I've been talking the last few minutes here, that the referential integrity enforced by that foreign and reference construct. They are naming a few things here, like you cannot update the key value. Well, you can if you are doing something that is called cascading, and that is something that you configure on your table. So if you are updating something that is being referenced, then that reference will also be updated automatically by your SQL server. And the same goes with cascading when performing a delete, but that might be a bit worse off. Yeah. So if you should remember just one thing here, just remember that cascade thing, I think. And there are a few things here that you can also program automatically using the SQL server. That's the on delete and on update actions, which means that there are a few other things here as well. There are on update, where you can program your server so that if a specific row or a multiple set of rows are updated, that will kick in your sort of SQL script, and you can do a few things before committing the things here. That is not something that we should be talking about in this course because it kind of gets messy and people tend to forget those things, that there are a few scripts running in the background. It's really, really confusing. Right. Okay. Let's see here if I can. Yeah. Let's skip over to. I told you that I should notify you when flipping over to the other presentation. Well, this is the time. Yeah. I'm flipping over from page 47, 46, 45. So let's see here. So we have been talking about those functional dependencies, where there are a few attributes being dependent on one or more other attributes. We mentioned the word determine, where one or more attributes might determine some other attribute. And we have been talking about those referential integrities and the key and the super key, the primary key and the foreign key. So somehow we have managed to create a model that sort of works. We just have to step over from the logical model over to the physical model, where we start to actually create those tables. So the question comes, when you have a many-to-many relationship, what do you actually do with that many-to-many relationship? Well, I think I've hinted to you that that relation R1 has to do with this in the end. So if that is your logical model, entities 1, E1 and E2 related to each other through the relation R1, what will actually become of it? Well, it turns out that it becomes 3 schemas or 3 tables. So this is something that you create in your SQL server. You start off with your entity E1. You have your attributes A and B. You have your attributes A and B. A is the primary key, it's the key. You have the entity E2 that has 2 attributes, C and D, where C is the primary key. And we have through our model told our project or our staffer in the project that, okay, E1 can consist of many E2s and E2 can consist of many E1s. So there's a many-to-many relationship here. So how do you create that many-to-many? If you have a look at the relation R1, which has an attribute E, we actually create a table of that R1. And we pick the keys from both E1 and E2 and move it into the new table named R1. So the key for R1 is consisting of the attributes A and C. And it also had that attribute E. Well, it's just an attribute, just a column, so let's add it. So going from that model and turn it into tables takes you here. And what you also have here, if you make things correctly here, is that you have foreign keys here, because the attribute A is referencing the A you find in the table E1. But if you don't make those constraints in your SQL server than they are just here on your paper. So that went from 2 entities and a relationship into 3 new tables. And if you have a one-to-many or a, well, many-to-one, saying that we have the same entities here, but we change the multiplicity on the one side here, saying that E1 can exist of exactly one E2. That is, we have to move over one of the keys from one side over to the other to make this work, and it ends up with just 2 tables. And I think I've actually turned it around. I'm stating here that E2 can consist of many E1s. So, isn't that wrong? No, it's correct. It's right. It's correct. Yeah. Sorry. It's correct. And once again, you have a foreign key here, and that is the attribute C in E1 is referencing something that is a part of E2. That's the C here. So that is your connection. So now, if you implement that correctly, you can start to ask your 2 tables for things, because they relate to each other through those 2 tables and that foreign key. Okay? So that's many-to-many and many-to-one or one-to-many. Sometimes you add more attributes to it just to fix it so it goes a bit faster when you're sort of violating the normalization, which I will be talking about soon. But once again, when you start to add redundancy, you are doing it by design, not by mistake, because that's a terrible mistake. So if you have a one-to-one, well, it depends. It depends on what you want to do here. Sometimes you can just add those 2 together and make just one table of it if it suits you. Or sometimes you add one of the attributes from the table over to the other one, but you don't enforce it as a part of the primary key. It's just a foreign key. So if you have a look at that one, E1, that's just a foreign key enforcing the one-to-one relation here. So sometimes it depends on what you model here, on which side it should be, or if you just go with one table. You're the one who knows this.
So the C will be here also a foreign key, so it should be a line under.
No, it's just that you can have only one row of it.
Mm-hmm.
It's just a one-to-one. So the model doesn't allow us to specify exactly how we want it, how you actually implement it using tables, because we're talking tables here right now, or at least schemas. And I find myself mixing things when I have those one-to-one relations. I'm flipping the attributes over from one side to the other because I cannot decide what I want to do with it. And that usually means that I haven't understand the problem itself. Okay, so those are the three ways of converting your logical model into a physical model. Many-to-many, one-to-many, many-to-one, and one-to-one. And what's usually confusing is that many-to-many and one-to-many, or many-to-one. They are just tables in the end. So, any questions to that? Good. Moving over to the concept of normalization. And what that means is that it is just rules for designing your relations. You remove redundancy and you remove unnecessary relations. And you also save space in the end. But the penalty is sometimes speed. It takes a bit more time to complete your queries. And there are a few rules here, and they are called normal forms. And what we will have a look at here is the first one through the BCNF voice code. And most developers say that, okay, our model should conform to no more than the third normal form. Let's skip the BCNF. And some people say that, okay, we should go to that BCNF level. And there are a few more ones. I think there's 6 of them. And some of them might sound strange, and some of them aren't. So that is the 2 rules that you must meet when putting something into the first normal form. So the first sub-rule here is that your data should be stored in a 2-dimensional table. So if you have your in a 3 or more dimensions, you are not following the first normal form. And I don't think that you have thought about creating a table in 3 dimensions yet. But if you're conforming to this one, well, just stop. And the second one here, the second rule here is that there are no repeating groups allowed. No repeating groups are allowed. So the first one is usually quite easy. The second one is sort of easy. So let's assume here that we have that table employee having the columns emp, first name, last name, and phone numbers. So is it 2-dimensional? Yes. Check on that. The second one, do we find any repeating groups here? Yes, we do. Because we are trying to store 2 numbers for Carrie Fisher. So that's a repeating group. And if you do that, then you don't have your table in the first normal form. So you need to do something about it. And some people, they like to do it they like the idea of adding a few more extra columns instead. And that is generally a really bad idea. Because if you have added an extra one, so you have the possibility to store 2 phone numbers, then you can be quite sure that the week after there will be an employee having 3 phone numbers. So creating those extra columns for trying to meet the first normal form is generally a bad idea. So you need to find another way of doing this. And the same goes with those. There are some people sometimes that they are so unsure about their tables, so they start to add column 1 and column 2 in case they need some extra columns. That is also generally a very, very bad idea. So if you find yourself doing that, you need to take a break and figure things out. So what you do here is that you take your employee table and remove that phone number column. Then you create a new table called phones, where you have that employee number and the phone number as your attributes, because then you can add as many phone numbers as you like for a given employee.
And we are still in 1NF.
Yeah, when you have done that splitting, you are in 1NF. But as you can see, there are no keys here, but that's not a part of the first normal form.
We are not considering the employee a key here?
No, not at this. As in terms of the first normal form, it doesn't care about the keys. It only cares about those repeating groups and being in 2 dimensions only. Mm-hmm. So that second normal form takes care of that. Mm-hmm. So if you are to put your table in the second normal form, then you must first set it into the first normal form. And then you have to make sure that all your non-key attributes are functionally dependent on the entire primary key. So if your attribute is not part of that key, it must be functionally dependent on the entire key, the entire primary key. So let's have a look at this car owner table, which is meant to store cars and their owners. So it's in the first normal form. I haven't any examples here showing you data, but we can assume that it is in the first normal form. So if we have a look at those attributes that are not part of that primary key, and the primary key is consisting of 2 attributes, register number and owner ID. That's the primary key. So the start date of the ownership, is that functionally dependent on the entire key? Well, I've taken this table out of context, so some of you might say no. But as for my part, it is so. It is functionally dependent on the entire key. But if you have a look at the last attribute, owner phone, is that functionally dependent on the entire key or just a part of it? It's only a part of it. Because the owner phone number is functionally dependent on the owner ID. Which means that this example is not in the second normal form. Another way of saying is that the owner ID is determining the owner phone. And so there's a missing line here. I don't know why it is so, because I can see it on my screen here. So sorry about that. There should be a line here. So we need to do something here. We need to put that table into the second normal form, and that is done by making another split here. So we are trying to remove that owner from that car owner table, the top one, the one that is not in the second normal form. And then we are trying to make that owner phone being functionally dependent on the entire key of another table instead. And that other table is named person, which means that the owner phone is functionally dependent on the person ID, which is the entire key. So that's okay. Making that owner ID a foreign key makes us puts us in the possibility of asking the person table for the phone number of the specific car, for the owner of that specific car, because our association goes through those two. Even though the name is different, they mean the same thing. It's a person ID. Can you see that? The name of that attribute doesn't have to be the same in the original one. They need to mean the same thing and be of the same type. And then you are enforcing the integrity using your SQL commands, and that makes it possible to say something like, okay, you cannot create a car without having a person first, or something like that. If you should be able to have an ownerless car, well, then you cannot put that one to be a reference, because you might in that case referencing using nothing. Okay, should we go for a 10-minute break? Okay. Right. So if a person have more than one phone, would you add another column here? Or would you split it into another table? So first of all, I don't think that owner phone is a very good name. But if I need another one, should I do that?
Wouldn't that violate the NF2 NF and second NF, like the first part?
Yeah.
That is not.
So if we need another phone number for some reason, we will not be adding another column here. We are then in that case forced to create another table holding those phone numbers for us. Because sometimes you put your example or your table here in the second normal form, and that goes for the car owner, but the person might be violated later on when you start to add things. Okay. Right. And the third one, well, first of all, you need to have it in the second normal form. And then we have that rule that says that there are no transitive dependencies. And that means that there shouldn't be a way of making functional dependencies between the non-key attributes. So we have our key here, our employee. We have our person ID, which is, I think it's called SSN, Social Security Number, on the other side of the pond. We have our home address and that personal phone number. So can we find something among the non-key attributes that has a dependency between them somehow?
All depends on the person ID.
Yeah. The phone number and the home address is depending on the person ID, and that attribute is not a part of the key, because the second normal form just checked that you were depending on the entire key. This is among the non-key attributes you're looking right now. So if you have this situation, you need to do something about it. First of all, is there anyone in here who doesn't see that there is a functional dependency between the personal phone number and the person ID, and also the home address? So what you do is that you split that employee table into two, removing those depending attributes and add them to your new table. And that ID that you see in that person is the person ID that you find in the employee table. so that you can create a query that can find your relation here.
But in this case, we are forced to use employee as employee.
Yeah. I made that example just to show you what can happen here. So the table itself or the schema itself might be out of context. So this is just for making a statement here. All right. And then on to Boy's cod normal form. So the first one is, okay, make sure you have your table in the third. And secondly, all your determinants should be candidate keys. That's the rule. Which means if you think for it a while, and this is really a created example. It's really hard sometimes to find a good example for it. But I think I mentioned this example earlier, where I had that car inspection, that yearly car inspection that every car goes through. And I thought that, okay, let's create a table for that, where you have your appointment here, your car inspection appointment, where you have your register number for a car, you have gotten an appointment number, your time and date is set for it, and you also know who is going to inspect your car. So we're looking for those keys here, or those attributes that are actually pointing the other way around. Is there anything among those non-key attributes that determines the whole or part of the key instead? So I'm not talking about dependencies, I'm talking determinants. Attributes that determine another attribute. It's the other way around. Well, it can be quite hard to see it here, but
maybe the time.
Yeah.
And the appointment.
Yeah.
Because like if they go from day to day.
Yeah, exactly. That was my idea here. So time is determining the appointment number. So and time by itself cannot be a key. So it is not part of the candidate's keys, but it determines something that is a part of the key. So we are violating Boy's code. So if we instead create, oh sorry, it shouldn't be car inspection once more. Sorry about that. I'll fix that. It should be inspection time or something like that. This is a really constructed example, as you can see. We're removing time and the appointment number from, we're removing the appointment number and setting time instead to be a part of the primary key of that car inspection table. Create a new one, which shouldn't be called car inspection. That's a copy-paste mistake from my side. Let's call it appointment time. Setting the time as the key and the appointment number to be determined. And we are not violating the Boy's code normal form. This is quite unusual that you have this case where you have a non-candidate key determining something that is part of the key. That's why I think that most people say that let's just go for the third normal form and skip the rest, because they are quite rare special cases. Okay.
In this case, how do we determine the appointment number from that?
Well, there are some restrictions here. I think that there cannot be that many booked time and so and registers as such because you can only have one time here. So the time here must match, and that way you can get the appointment number. So if you somehow manage to get 2 appointments at the same time, this one will not work because the primary key will enforce that you cannot add a duplicate of that time instance of that row. All right? Okay, back to the original slideshow. So that was the main theme for today. Trying to discuss those keys and dependencies, those attributes that determine other attributes, converting entities into tables, those 4 normal forms, 1 through BCNF. There are quite a number of slides left for me to show. I will not do it. I will just walk you through a few of them, and the rest is there for you to read. And I should also mention that I will remove some of them. So have a look at that PDF tomorrow, and you will probably find that there are a lot fewer slides in there.
And it is enough to check the slides and read from them, right?
Yeah.
To form an idea about the course.
Yeah. If you want to, I can mark them. I can leave them there and mark them as a sort of a secondary reading if you're interested. Because there are some really interesting stuff going on here. And once you start to work and you have been working for a while, you need to take those things into consideration. At least most of it, not all of it. And what we are talking about here is that performance and the storage space and the reliability, because if you have something that isn't fast enough, you might be in trouble, especially if there are personnel involved that might get hurt if your database isn't answering fast enough, or if your queries are performing too slow because you have made them too complex. And then also the storage space, which might not be a problem these days, and not, well, the reliability is a must here, because your server might, let's assume that your server runs correctly in 90% of the cases. That is not very good. So 10% of the cases, it's faulty. It's making bad decisions. That might go for the engine itself or the server itself. So the server, the machine, stops, which breaks everything. So you need to understand where your database is actually running and what the purpose for that database is. Because if it's just a database for storing pieces of information that will be retrieved once every second week, and it is not that important whether you can retrieve it or not, well, then you might go for a slower machine, for instance. You might not be needing that 16 gigabytes of RAM, or even more, or a cluster of database servers. Let's assume you're buying a cluster of database servers and you're paying 20,000 a month for that retrieval you do every second week. You're overpaying. So make sure you know why you are using your database. And this is another topic, and that is of trying to figure out how much data you will be storing in your database. And that might not be so easy. This is sometimes it's sort of a guesstimate, if you would like to call it that. You might be asking, let's assume that you have that company that you're working for, so you can go and ask people, how many times do we change things or add things? Do we get any new customers, or do we delete them? And then they might say, okay, we're adding about 100 new customers a week. Then you can sort of estimate how much your data, or how fast your database will grow. I don't think that you have thought about that before, and in most cases, when I am having a simple task with a simple database, I don't think about it. If I have a disk, a terabyte disk, and I'm just storing a few bits and pieces once every second month, I don't do these estimates at all. Just a feeling for it. And also, sometimes you need to think about how data is actually stored and fetched, because you might want to set index on some tables and some columns, so it is really fast when retrieving data, but a bit slower when adding data. So if you talk to one of those DBA experts, they are really good at telling you what to do or what not to do. But as long as you know that, okay, using indexing might speed things up, but there's a penalty. So if we go back to that model where we had the movies and the stars, and that stars in relation, how many rows per table? That's just a guess. There's that database, IMDb. If you need to know something about an actor or a movie, that's probably the place you go. And you create a search and look at the text or the images. So this is just an estimate. So let's assume that there are 1.8 million rows in that movies table, and there are 2 of them in the stars, which probably, because this is a many-to-many relationship, which meant that that stars in is actually a table having what as the primary key in here. If I would create a table of that, what is the primary key in here? Well, you pull the primary keys from the other 2 entities. So the primary key here is title, year, and name. So you need to combine these 2 and come up with the calculation that around 15 million entries are found in that stars in table. So I hope you can sort of notice here that there's just a way of thinking. I am estimating, I'm guessing how much there will be in here. And I should also point out that I would really like to know how fast they grow. Do they increase or do they decrease? I have no idea. And also, that database or that site, the site is using that database, by the way. Your database is used by that site, IMDb. If that site has, or in this case, we could say that it just is the database. It has 100 million accesses per day. Then there are a lot of accesses going on here. So we can assume that there are 100 million searches for movies, and 5 of them also goes to the search for one or more actors. So if I have a very large table, it might be so large that it is taking too long to find an entry in it. And if that is the case, you might add some extra performance, some extra CPU power, or a faster disk, or more RAM, or you might start to dribble with that movies and split it into different tables based on some criteria so that you can search in them faster. At some point you need to be inventive, or your searching, the way you are allowing your users to search might be wrong. So there are several ways of making things better, but you need to first of all trying to estimate how much of things here. So let's just have a look at the last one. If a visitor access, let's say 2 actors per movie, so we have 10 million access to the movies table, resulting in 20 million access to the stars table. So there's an effect to things. If you start to search in one of them, then you have your query querying over to the other one. And do you remember when you had that that joining, when you are, let's say we had that cross join where we join just about anything, that will be quite a big table in your RAM. Or if you are, I think you would probably put things on it on the hard disk anyway. So using the correct form of join here might help you speed things up. But as long as they are small, your tables are they contain very little data, you will never be aware of the problem until they grow. And sometimes they grow exponentially, and then you're sort of in trouble. So if we have figured out how many times they will be accessed and how many rows a table contain, we can try to figure things out a bit more. And that is based on those attributes, because we know the type of we know the types of those attributes. And if you know the type, let's say it's a float or a double or a real, that was 8 bytes in that case. And if you have let's say you have an integer ranging between minus 128 and 127, then it's a byte. So as an example, if your title might contain at maximum 300 characters, and the year is 4 characters because we choose to make a character of it instead of an integer, because an integer took perhaps too many bytes here, or perhaps it just felt better to make a 4 characters out of. So that's something you should ask the creator of that table. Why did you choose characters and not an integer? The length is an integer. The film type is a maximum 5 characters, and the movie ID is an integer. And when you know that, and that's the SQL version of it to the right. I don't know if you remember, when you put that as a character, it will be 300 characters long. It doesn't matter if the title is containing 20, it will be 300. So some people make that an n character, an n var character instead, which makes it variably large. It uses no more than it needs. Right? Yeah. So suddenly you can calculate the amount of bytes that is required per row in that movies table, which returns 315 of them. And then there are some overheads, and that is to maintain and manage that table. And that depends on your vendor's database engine. So if you're using Postgres, you are adding another 24 of them, returning 339 bytes per row. So if we had 1.8 million rows, this will add up to, or amount up to 610 megabytes. So if you know the rate on how fast it decreases or increases, you can predict the future, because this is what you might have right now. But you don't want to change the hard disk or the storage in 2 months just because you couldn't predict the future good enough. Or, as most people actually do today, we just put it in the cloud, and there's someone else's problem. But I should also point out that there are many companies out there that doesn't use the cloud for storing things and running things. Okay. Let's skip that. Any questions? All right. The next lecture is on Monday. Okay, thank you for today.
Thank you.